Hey everybody, we're talking about the tau function again tonight. The tau function is a number theoretic function that just counts the number of divisors. Now let's look at a concrete example of what a tau number is. 2601 turns out to be a perfect square. It's equal to 51 squared. Now you'll notice that 51 is the product of two prime numbers, namely 3 and 17. You can see that right down here. Now this tau number theoretic function, again, it counts the divisors, but it's also what they call multiplicative. You can split it. And so we'll write this tau evaluated at 3 squared. I'm just making it like a lowercase good old American t. And then tau times 17 squared. Now this isn't, just the notation's a little weird, I guess, but notice that 3 squared has exactly 3 divisors, namely 1, 3, and 9. And so this would be equal to 3. And the very same thing holds for any prime number. 17 squared has 3 divisors, 1, 17, and 70 squared. So you get 3 times 3 is equal to 9 here. Now notice that meets our definition of a tau number. 9 does divide, or 3, it's easier to see that, I'll just write it down. Tau at 2601, tau evaluated at 2601 divides 2601, and that literally is the definition of a tau number. So tau is getting used in two senses here, as a number theory function that counts the divisors, and also as a certain type of number. So we've just established that 2601 is a tau number, okay? Now, as far as this problem goes, and we'll get into it, we'll prove it theoretically here, but notice that P would be 3 as far as this example goes. P is equal to 3, and Q would be 17, P and Q being primes, okay? Now, but we want to prove it in general, and so it's actually kind of nice how that works out, how it does work out. We'll let m be the largest exponent such that q to the m divides n, and it's given that q is a prime divisor of n, that n has the smallest prime divisor of p, okay? And so based on what you saw right here, we incremented, 2 got incremented by 1 to 3, 2 got incremented by 1 to 3 here. So in the very same sense, m is going to get incremented by 1, and that means the factor n plus 1 will be a divisor of n, since n is a tau number, and n plus 1 is part of the total divisor expression, okay? That part's slightly tricky, but it makes a lot of sense. N plus 1 has to divide n, since n is a tau number, and q to the m divides n. And so remember, just like we incremented here, we have to increment here. So n plus 1 does divide n. Now what does that tell us right here? Okay, that tells us that m is less than or equal to p minus 1. But since m is the largest, you see m is the largest such, we get quickly that since, it's the largest one, m has to be less than or equal to p minus 1, so that means m has to equal to p minus 1. Since it's the largest, right? So m is equal to actually p minus 1 here. And we've actually proved what we set out to prove. We set out to prove that q, remember, q to the m, well, m is equal to p minus 1, so you see we've proved our result right here. That is, we've shown that q raised to the p minus 1 divides n, okay? Q raised to the p minus 1. That's certainly not a 9, guys. That's q raised to the p minus 1 divides our n. Okay, and so that's the end of the proof. And again, you can verify that's exactly what happens in this numerical example, right? 3 was the smallest prime, right? 3 was the smallest prime, but p minus 1 is 2. Okay, and so we see that 17 squared, which is 17 to the p minus 1, does divide. So it's all good. And that is the end of the proof. Let me write down QED here. Have an excellent evening.